Hello and welcome to lesson 5.5, continuity. So today we're going to actually look at when functions are continuous or when they're not continuous. So first of all, the term continuous, if you remember, is where there are no holes or breaks or vertical asymptotes or things like this. So in this function, you can describe this function to have no holes or no vertical asymptotes on all parts of this function in different ways. So you can describe it using interval notation, so from negative infinity up to the value of 3, because at the value of 3 you see there's a hole. Then from 3 to the value of 6, and then from 6 to infinity. Sometimes they'll even change these symbols right here, these commas, to little U-like shapes, meaning union of the values. Now there is another option, and I prefer this one more. You could just say x can't equal 3, x can't equal 6, and x belongs to all the real numbers otherwise. I find that a little bit easier to work with. So as you can see, this function shows you that your limits are not the same as you approach from the left and the right for this part right here, and also this part right here. Only when the limits are the same as they approach from the left and from the right for your function, you get spots where you have discontinuity, okay? Although this limit right here does actually exist, the value at that point also doesn't exist. So we're going to look at continuity and the definition of it today. So for a function to be continuous, first of all, the limit must exist. So limit as x approaches a from the left for a function must equal the limit, which is equal to the limit as x approaches a from the right for that function. So that has the first definition, and that's also the same definition for whether a function is actually having a limit exist. The second part actually states the value f at a actually has to equal that value L. So in other words, not only do the limits have to exist as they approach from the left and the right, but the point must exist at the exact same spot. So if the function is not continuous, a function is said to be discontinuous or have a discontinuity. Okay, so moving right along. Let's take a look at this function. This is called the greatest integer function, also called int of x. It's a common function that some universities use. Another way of looking at it, or another name for it, is called the floor of x. And I've also seen it described as f of x equals this, with this type of brackets. It means you take any function, any value, and find its lowest integer. So for instance, if you have f at 1, that is equal to 1. F at 1.5 is also 1. F at 1.9 is also 1. But f at 2.1 is now 2. So what you can see right here is we have various different spots where this function jumps from one value to another. As the limits don't turn out to be equal to each other, it's discontinuous for x values that are actually integers. So when there's an integer, let's say 1 or 2 or at 3, you see that's where the discontinuity occurs. If x is a real number, but x does not belong to an integer, then f of x is continuous. So as you can see, you can describe this in two ways. You can actually describe where it's continuous, and you can also describe where it's discontinuous. Okay, so let's take a look at some discontinuities. The first example, to the very top left, is called a jump discontinuity. This occurs when your limit, as x approaches the left for your function, does not equal the limit as x approaches a on the right. However, they do equal values. Okay. Top right function is what is an example of a infinite discontinuity. This occurs when your limit as x approaches plus or minus your value for a. Oh, my apologies. Let's rewrite that in a different format. Misstated it. As x approaches a from the left for your function g of x is equal to plus or minus infinity, which is also equal to the limit as x approaches a from the right. So in other words, it's approaching a very large value. This next one in the bottom left corner is what we call an oscillating discontinuity. So this occurs when your actual limit doesn't actually exist to be one specific value. It's so hard to tell where that value is. So the limit as x approaches a from the left or from the right, and this function h of x is somewhere between plus or minus 1, but you're not exactly sure where. And because you can't narrow it down, you just have that impossibility to solve for. The last case, I'm going to change to color purple here, is what we call a removable discontinuity. This is probably the only one that actually could work out. This works when your limit, as you approach from the left and from the right for your function, actually equal each other. So they actually approach the same value from the left and from the right. The only way you can fix it is if you define if y of x has the point 2 and -1. So you can redefine it if your function actually has that point. And if it has that point, then it's continuous. Okay, so some properties of continuous functions. This is a theory. Theories are always going to work for all types of functions. So if the functions f and g are continuous at point x equals c, or an x value equal to c, then the combinations are also continuous, also at x equals c. So if you add the two functions, if you subtract the functions, if you multiply the functions, you divide the functions, even when g of c doesn't equal 0, and if you take any function multiplied by any constant. Another theorem: if f is continuous at the value of c, and g is continuous at f at c, then the composite g of f is also continuous at c. So let's see how that works out. So what we're going to do is we're going to show that this function is continuous. So first of all, note y equals the absolute value of x is continuous. So if we had just looked at this overall function, we notice that's continuous. Now we just need to show that all the other parts in pieces are also continuous. So also y equals x is continuous on all x belonging to real numbers. Y equals cosine x is continuous for all x belonging to the real numbers. And y equals x squared plus 1 is continuous for all x belonging to real numbers. You may also notice x squared plus 1 is always greater than or equal to, greater than 0. In fact, it's always greater than 1. So it'll never equal 0. So, therefore, the function y equals absolute value of x times cos x over x squared plus 1 is continuous for any real number based on those theorems that we just saw. Another theorem is called the intermediate value theorem. What it does state is if you have a function, y equals f of x, that is continuous on a closed interval from a to b, so in other words that has no holes or breaks or spots, then the function f at a takes on every value between f at a and f at b. So if you have some value c, let's say, that is between a and b, then f at a is always less than f at c, whatever f at c might be, which is less than f at b. So there's actually some values in between there. And this helps allow you to realize that there could be zeros or values in between a high value and a low value. So let's use this intermediate value theorem to prove that there is a root for the function x cubed plus x plus 1 on the interval from -2 to 2. So in order for there to be a root for the function, that means f at x, there must be some value c that equals 0. Or if you wish, x cubed plus x plus 1 can equal 0. Well, first of all, f at -2. If we actually substitute that value in, we work it out, and we get a value of -9. If we work out f at 2, you get the value of 11. So therefore, by the intermediate value theorem, you can use the IVT as an short form. -9 is less than f at c, which is less than 11. So therefore, the value of f at c equals to 0 exists. And we'll show you how you can actually find that value of c later on. Okay? And thus concludes this lesson.